Good. It's just techniques. Good. Anyways, so let's see. Record is started. Yes, you have the wrong slide here. So that's what I wanted to show. Okay. So welcome everybody. Sorry for this. So people are filling up the open slots here. We have now a couple of additional topics suggested. So Mr. Grothaus, how is it spelled? Grothaus? Okay, I apologize for any misspelling here. So the idea of Voyager to the ISM, this is really a nice topic. Thanks for that. Do you have any, so is he here? I think I saw him here. Is he, do you have any like references, or do we need to find something there? Okay. Good. So, well, end of January is some time. If you, let's say, if you don't find anything till next week, so maybe I can also start looking, or we can together try to figure out something. So very nice topic. Then we have some shifts in dates. So we will have no talk in December. Okay. There is one open slot for Mr. Fischer. So, yeah. So we need a topic there. If you don't like what you see on the web page, then we need somehow to figure out anything. So maybe, so within the next 1 or 2 weeks that we can agree on something, because then it's only 4 weeks left, which is on the lower end, I would say, as preparation time. So this is just as a reminder. Then I need to briefly check my notes. Okay, so Mr. Pfeiffer, if you could stay after we finish, just for 5 minutes, that we talk about like the Prüfungs regulations for you.
Yes, sure.
Good. So, okay, so with that out of the way, we, in the last weeks, I always presented some additional computations, examples or so. I don't have this today. I have more questions for you to discuss. So let's see, we have 2, 4, 7 people. I need a brief poll here on what you would prefer in terms of breakout room sizes. So my initial idea now would be to have 2 breakout rooms, so one with 3, the other with 4 people. I got a remark that some of the rooms are on the lower side of attendance, so that the discussion tends to be kind of under complex. I think 7 people is a little bit too much for a discussion, but we can test this so that we just have 1 breakout room. So what would you prefer? So maybe if you write in the chat a 1 or a 2 for 1 or 2 breakout rooms as your preference. Good. So 6 yes, 1 no. So maybe what would be an argument for yes?
thought the photon has itself an angular momentum. And if you emit one, you always take some angular momentum with you. So you can't emit a single photon without changing the angular momentum.
Okay. So you argue with angular momentum conservation? Mm-hmm.
Yes.
Okay. Very good. What is any other arguments for yes that came up during the discussion or that anybody has in mind? If not, what would be the argument for no if the one person that voted no wants to lift the anonymity? Okay, I don't see anything, so maybe I'm blind here. So let's see. To be honest, I'm somewhat unsure about the answer here. So my first reaction was the same as mentioned, that the photon carries angular momentum, and of course, in that case, conservation dictates that the total angular momentum of the atomic system needs to change. So yes. But this relies on that the always cannot be the case, was here the argument. Why not? That's a weak argument. So guesswork is, so it doesn't feel right, is weak. Okay. But this relies on the assumption that every photon carries an angular momentum. Is this true? Do photons always have, well, they have energy, naturally, but do they also always have angular momentum?
Don't they need to be polarized in that kind of rotating way to have an angular momentum?
Yes, I would assume so.
So that would mean no, they don't have to have an angular momentum.
Well, if a photon is linearly polarized, I don't see it carrying an angular momentum. Is this right? So, well, your quantum mechanics is probably more like solid than mine. So I would assume that a photon not necessarily carries an angular momentum. Can somebody here argue in favor of this or against this? So when I look at the interaction terms that I wrote in the lecture notes, and we have this series expansion. The first term is E, so just the charge, times r dot, so the change of the dipole moment. Generally speaking, I don't see how this would automatically imply the creation or the destruction of an dipole, of an angular momentum. So I would argue no. But the overall idea that you presented, namely that if the photon carries an angular momentum, then yes, then so that's something that I would like also agree to. Good. So anybody wants to remark on that? If not, we can like continue. Okay, so apparently not. So let's see. I have a couple of other questions prepared. Let's see what we do. So, and that. What do we have here? Okay, so let's do. Ah, damn it. Let's do that. I copy as. So before we go into the next breakout session, should we leave it at one room for all of you? Okay. Okay, so I stop this here. Okay, like 6-1 for power of 2 versus power of 1. Good. Why power of 2 or power of 1? So that would be my question here.
Because in the lecture notes we found a formula that gives A as a formula that is dependent of omega to the power of 5, and further up we found a formula that says that V is dependent of A times some factor dependent of omega to the power of 2, but no, to the power of 3, right? Yes. I just realized that you asked for the frequency and not the wavelengths. So maybe I would change my vote to the power of -2.
Okay, but leaving that aside, let me briefly see something. Okay, so that was here the chain of argument, and my green screen crashes. What's that? Good. And who was arguing, or what's the argument? Or anybody wants to add to that? No. Okay. I would argue it's to the power of 3, because when I check when you look at the lecture notes, we have here the case that the induced emission depends on the interaction operator here times the frequency, and it depends, is the frequency to the power of 2 times this is to the power of 3. And I would argue that it has the same frequency dependence as the spontaneous emission, because actually it's the reverse process. And if you consider equilibrium situations, so that you have a balance between all emission and all, so it's no, that's actually, it's not true, so forget that. No, okay. And you were arguing BAA. No, actually, I think I'm mistaken here. So what was my question? Electric quadrupole transition. I saw it. This is dipole emission here. For the electric quadrupole, the omega, the Einstein coefficient, the A coefficient goes with the frequency to the power of 5. And it relates to the Einstein coefficient via this formula. So this is general. And so we have to divide by the frequency. No, it's to the power of 2. Ah, okay. Ignore what I said. So quadrupole. Is this right, what I'm thinking here? Or is this like, am I running in the wrong direction?
Well, that's what we are going with.
Okay.
Exactly the same that we are
Okay, good. Okay, good. So then we are, yeah, no, I was lost here. Good, forget it. Good. Beenden Sie. So let's see. The next question.
So the frequency dependence is proportional to the power of -2, right?
Plus 2.
Yeah, but yes, but I thought that's the
wavelength.
it's wait.
Yeah, it's
Okay,
omega,
yeah.
it's a frequency.
Yeah. I confused the variables.
Genau. So what is a nice question? Let's see. Was here? Yeah, let's do this. Okay. Okay, where's the chat? So here we are. Okay. Question number 3. So now we are one person more. So is the size of the breakout rooms okay? Does everybody has the feeling that he is able to participate reasonably, or should we split into 2?
The size is okay.
Okay, so let's keep it. Good. So what would you expect? What is the difference between the electronic lines, Balmer alpha transitions, between hydrogen and deuterium? So let's start the thing. Yeah, good. Okay, so that gives an overall idea a little bit on. So this is the result. Okay, so why are they the same? So if you have an argument why they need to be the same, that would be the point to present it.
They are, because it's independent from the mass and only dependent on the charge of the core. The energy levels of the Bahn of electrons.
The orbit then, okay.
The orbits.
Okay, so this is the argument because they are the same. Because the charge is the same, and it only depends on the charge. Okay, so that means this is an argument that the other three people didn't share. So what would be the argument for the two frequency to be different?
That the core has a different magnetic moment. So pure hydrogen has only possible moments of minus one half and 1/2. And if there are now a neutron and a proton, I can have a spin of 1 or 0. And that's different for the structure of the lines.
Okay, that is true. But why does this affect the Balmer lines? Because here we are talking about the main quantum number, basically. So the pure electron orbits.
Oh, since I'm mistaken.
I'd say it could decay from one energy level to another, and the energy levels, the upper and lower, are splitted by. So we have effectively two energy levels very close together on which they could land.
That's true, but this is also true for regular hydrogen. They also have, because the electron has a spin. So we will come to that. So when I look at the, let me change this here. So this is from the lecture notes, right? So this is basically the energy of a certain transition. So that depends, of course, of the quantum number n. So what shell do we have? It depends on the charge. And when we compare deuterium and hydrogen, that wouldn't change. So it all boils down, does deuterium... So when we take a ratio between En minus En prime of hydrogen over En minus En prime deuterium, this is exactly the answer to the question, right? Because energy is h times frequency. So this is basically the frequency ratio, the ratio between the two transition frequencies. And everything cancels out. So the C cancels out, this parenthesis term with the quantum numbers cancels out. So the only thing that we have left is the ratio between the Rydberg constant of hydrogen over deuterium. Would you agree? So is this right? Am I making a mistake here, or? I don't see. Who doesn't agree? Nobody.
I agree with this explanation.
Say again?
I agree with this explanation.
Okay. So now the Rydberg constant is given by this expression. And it contains the reduced mass, because the two charges are orbiting around the common center of mass. And the reduced mass is different for the deuterium and the and the hydrogen, right?
Yes, it's roughly double the size.
No.
Not double?
Well,
because the electron doesn't weigh anything, and
Yeah,
I
yeah,
have my
yeah, yeah.
two.
So let's see. Exactly. But if you put in the actual numbers, it can. So well, I wrote this down somewhere. Let's see if I find this. If not, then we have to do this as exercise. Yeah, here. Let's see. Can you see this? So what we have is basically then the ratio between, this is the reduced mass for the hydrogen. Can you see this, or is it too small? Let's make it bigger.
Too small.
So this works.
Better, but the blue stuff is not visible
What?
in the bracket.
Now?
Better.
Okay. So this is the ratio of the two reduced masses, and here I'm even like putting in the same numbers for deuterium and for is this right? I'm not sure if this is the same number. No, I'm putting in the a proton and the deuterium, the neutron masses, and when you compute this, you find a difference that is in the order of 10 to the minus 3. So a slight difference. Now, whether you argue this is the same or this is the difference by, well, okay. So my argument would be they are not the same. They differ very, very slightly. And if I'm making a mistake here, then just check this, and I'm always open for corrections here. So I would argue 10 to the minus 3 is the correct answer.
But what is the reason for that again? Is it because the potential of the masses, or what's happening here?
Yeah, what happens when the reduced mass changes? So I basically ping pong this back to the group. So all of you are much better in nuclear physics than I am. I would argue that deuterium has slightly different orbits than hydrogen.
Yeah, but why?
What would the others say? Like, come on, Frankfurt is like, everybody of you is much better in nuclear physics than I am.
Because I know for big isotopes, like for example gold, it's so big that it becomes relativistic, and therefore I have this yellow colored material. But the change is not so big. The electron shouldn't be relativistic or anything else. So.
Yeah, I wouldn't argue with large with large nuclei, because there you have a the point, you cannot assume that the charges are really points, and you have like the additional neutrons, like what do they do?
because I think in God it's really an effect of the masses here.
Yeah, like the others. There are more people here in the room. Everybody is much cleverer than I am. So what would you say? What is the how would you reason with your physical understanding? What principles would you use to argue here? Physical principles that you know and
Because gravitational interaction shouldn't
no.
make a difference.
Forget gravity.
Okay.
I would argue by just energy conservation, namely that when the reduced mass is higher, so when the nucleus is much more massive, then its orbit around the central around the center of gravity is naturally much different from a single proton. Consequently, the electron orbit is also different. I didn't write down the full two-body problem here, but of course this boils down again to the reduced mass expression. So when you put in the numbers, because you have to move the twice as heavy nucleus by the Coulomb interaction. No?
It makes sense. The Trägheit is größer.
The inertia, right.
Yeah.
The inertia is yeah, that's written here is the reduced mass, the inertial mass, right? Is this like come on, people, physicists? And so, do I need to look up what semester you are in so that we can have a?
Well, that sounds reasonable, but I'm completely confused right now.
That's good. That's exactly my purpose. Like, I mean, that's come on. This is nuclear physics lecture first day. The basic like hydrogen atom stuff. It's easy, right? Isn't it? So in that sense, this is a valuable discussion because it puts what you thought or what you understand to a test. Because it just makes a slight change. To this setup that you understand and that you can compute. And then you need to like figure out, okay, so yeah, this makes sense. So okay, so when I look at the time, I see that we are already past 1:30, so I guess we stop here. Let's give you some homework. Let's try to prove that I was wrong here. Take what you have from the lecture notes or what you know otherwise, and try to figure and try to make a point that they need to be the same and that I'm wrong. So that next week we can maybe spend 10 minutes if somebody has a good argument, and then I'm happy that I learned something new or learned that I was wrong all the time, which is even better. So, or we agree then, yes, that needs to be exactly like this. We put in the numbers, but I'm doing mistakes all the day. So in that sense, it's not unlikely that I'm entirely wrong here, which is like, that's how it is when you come up with questions that you can't look up the answers. So yeah, spend maybe half an hour, think about this, write this down, figure out, is the Rydberg constant different or isn't it? And if it is, would this give us a factor of 10 to the minus 3, or is it neglectable or whatever? Okay, so I think we stop here. Thank you for like participating. I really, so this is the whole point. So that we use this 1 hour, I don't know, 80 minutes or whatever to just discuss a little bit and bring up question marks in everybody's mind to yeah, like handle a little bit the topics. And when I'm wrong, and if you're wrong, then you're wrong. It doesn't matter, because we need to make mistakes for having some progress here. And I'm looking forward to some good ideas on whether 10 to the minus 3 was a good answer or not. So with that, I would like to stop here. Thanks for participating.